So in lecturette 2, I want to discuss why membrane potentials are important. And I want to do so is because all your predecessors have asked this question. Why and what do we use membrane potentials for? Now, membrane potentials are very, very important to run all the processes in our body, right? And so the first process that we can talk about is they allow membrane proteins to do work. Now, what does this mean? You already know. And let me show you, right? You remember secondary active transport? Yes, is where we have now a molecule that is traveling down its concentration gradient that's giving now kinetic energy to run a molecule to move against this gradient, right? And so this is the way then we can allow this protein here to do work. And in order for this protein to do work, shuttle molecules back and forth inside and outside of a membrane, right? Is we need to have a concentration gradient. And with the concentration gradient, we can now do work. Now, that concentration gradient is set up by what mechanism? You folks remember? Yes, it's from the ATPase, right? That sodium potassium pump that allows us now to have a disequilibrium of sodium outside of the cell compared to inside of the cell, right? That is now what we can also call an electrical gradient, is because when we now change the concentration of sodium, so there's disequilibrium, meaning that it's higher outside of the cell, I also not only create a concentration gradient, I create a electrical gradient, right? Is because here now I have a more positive charge outside of the cell, okay? So creating a disequilibrium to do work now is us making something called an electrochemical gradient, right? Creating a concentration gradient because majority of these are ions, it also becomes an electrical gradient. Here is another function that membrane potentials provide. They allow us to secrete stuff, whether it's a hormone or a neurotransmitter, any type of a molecule that is large via exocytosis. Okay, so I want you folks to look at this picture, and let's not get caught up too much on this picture because this is where we're going. We haven't arrived there yet. So some of this stuff we haven't even discussed. But the point of this slide is I want to show you how hormones are secreted. And if you are a big protein hormone like insulin, this is a mechanism of action to where you're utilizing the membrane potential in regards to its charge, but you're also now stockpiling, creating a chemical gradient of calcium outside of the cell. Okay, so if I want to have exocytosis, remember in unit 1 we talked about exocytosis, that I need calcium in order to have exocytosis. And the reason being, which we are going to cover in this unit, is calcium is going to bind to some proteins, the proteins that are carrying the vesicles, and allow them to have now a conformational change to drag them to the lipid bilayer. Okay, so in order to have exocytosis, you have to have calcium. But in order for calcium to come rushing into the cell, you have to actively pump calcium out, right? So you create now, if I have a pump, this is a calcium ATPase, I can constantly pump out calcium. And this will now lead to a high level of calcium outside of the cell. And I stockpile it. That's my concentration gradient. It's also now an electrical gradient because if I have a lot of positive charge out here, right, this part of the membrane out here is going to be positive. Does this make sense? Okay. Now, I open my voltage gated channel, which is going to respond to voltage within the cell. And as soon as this gate opens, I can have calcium rushing in and binding to these vesicles, which will allow us now to have the release of whatever protein that you're trying to exocytose. Now, the last example I'm going to give you folks is electrical impulses, right? And so for the nervous system, neuron to neuron or neuron to muscle, The nervous system communicates via electricity. Okay? And so these membrane potentials provide this electricity. And so what you folks are seeing here is communication between one neuron to another neuron, right? Via this electrical signal that we're going to talk about at the end of this lecture called an action potential, right? And this electrical signal that's traveling down this axon can be sent now to another neuron. And that's how we pass messages to neuron, neuron to muscle, neuron to gland, whatever the case may be. Now, electricity is just moving ions. That's all it is. So this is why you folks have to take chemistry before you took physiology, is because I don't remember if you folks remember all of your metals. Okay, some of you folks are rolling your eyes. Don't go there. I'm not going to test you folks on the chemistry, but if you folks remember the lecture about metals, is that metals have what we call a sea of electrons. And those sea of electrons can travel from metal to metal. That's why when you slice open any electrical wire that you folks have in your house, you see that the wires are metal wires, okay? It's because they allow you now to have that moving of ions to get electricity from the power plant to your light or your computer or your phone, okay? Now, the same thing is happening from neurons to whatever the next thing is, whether it's a neuron or effector, is all electrical signals. And I can have now the movement of ions that allow me to have that electrical signal move if I have now this electrical chemical gradient, okay? And that's where we're going next. I'll see you back for lecture at 3.